Thanks. Just what
I know that breaks are one of the fun part of these conferences, but we're on a pretty tight schedule this morning at least, because we have to conclude by 11:45 so you can listen to Jim Green's talk at lunchtime. So I hope that the folks who are outside getting their coffee will come back in soon. But I think that we're going to get underway. We have a very exciting panel coming up. There are 4 excellent papers that are going to be given. And it's a 2-hour panel discussion. There's no break in this panel discussion either, I regret. So if you need to get up, feel free to do so. But my main job here today is to keep the trains running on time so that we are, in fact, out of here by 11:45. And each of our presenters has had an equal amount of time to give their presentations. For those of you who don't know me, I'm Marcia Smith. I'm a veteran space policy analyst here in Washington, and these days I have a website called spacepolicyonline.com that builds on my very long experience at the Congressional Research Service, although I've been in a lot of other places also while I've been in Washington. I've actually been a space policy analyst for 40 of the 50 years that we're celebrating here today, so it's been quite a long time. But as I said, my job is to keep the trains running on time, and what we all agreed to is that each speaker will speak for 20 minutes, and then there will be a 5-minute question and answer period for that speaker. And that should give us 15 minutes at the end for a broad question and answer discussion. And I'm not sure where everybody is going, but maybe they're all going to have them march in here in unison. I'm not quite sure. But in any case, I am going to change the order of the presentations a little bit. Dwayne Day will be first, and then Jason, and then Roger, and then John and Andre. So there is a little switch there in the middle because it made the flow of the papers better. And just to remind you to, again, please silence your cell phones. And we, of course, encourage questions in between each of the speakers and then at the end. But as a courtesy to everybody else who wants to ask questions, when you do, would you please keep your questions very concise and directed at a speaker. So I'm going to start off with Dwayne Day. There are longer biographies for the speakers on the website and in your program, except for Dwayne. Dwayne gave the most concise biography I've ever seen. It was 1 sentence long, which says that he is, in fact, a senior program officer at the Aeronautics and Space Engineering Board at the National Academy of Sciences right now. But Dwayne is actually a very well-known military space historian, and he often writes for the Space Review, and I know Jeff Faust, who runs the Space Review, is here in the audience. There he is. Hey, Jeff. And so Dwayne is actually very well known in the space policy and space history business, and I'd like to invite Dwayne to come up now and give his presentation. And by the way, just so no one thinks I'm being rude, everybody knows that after they've spoken for 20 minutes, I'm going to come up here to the podium to make certain that they conclude so we can keep the trains running on time. Dwayne?
Thank you, Marcia. I'm reminded that this is a pretty small community, the field that we're in, and I was reminded of it even more when I looked at the agenda a few weeks ago, and I looked at my panel. Marcia Smith used to be my boss, and now she serves on a committee for which I am a study director. Also on this panel is Andre Bormanis, and Andre and I used to work for John Logsdon, who is also on the panel, and as well as Jason Callahan, who used to work with me at the Space Studies Board, and Jason now works for my girlfriend at NASA. And also on this panel is Roger Handberg, who I actually don't know, but I am sure that very soon I'm going to be working for you. So it is a really small community. And I also noticed that on the agenda there's a number of speakers who have worked on various National Academies studies over the years. In particular, a few of the ones that are up here. When I was putting together this presentation, I thought about throwing a whole bunch of covers from National Academies reports onto a slide, and I started to look, and it turns out that over the past 50 years, there have been something like 95 plus studies that the academies have done on planetary science. The exact number is somewhat iffy. But you know, that works out to almost 2 studies a year that we've done for NASA, a few for the National Science Foundation. I put 4 of them up here, and the 2 on the left were ones that I was directly involved with, and I think you can actually trace some you can directly trace some recent space policy decisions to the work that we did at the National Academy of Sciences. The one second from the left there, Opening New Frontiers in Space, we helped develop a list of possible science missions, that planetary science missions that could be conducted, and one of the missions that's currently under development, OSIRIS-REx, resulted from the work that we did on that study. The study on the left, grading NASA's Solar System Exploration Program, was a midterm assessment of the Planetary Science Decadal Survey. And that study, I think, deserves a fair amount of the blame for the cuts that the Mars program got a few years ago. That was not our intention. We provided a report card on what NASA was doing in space and planetary exploration, and we gave the Mars program an A+, said that they're doing a great job, and that was used by the then Associate Administrator for Science as an excuse for cutting the program, because he figured, you know, A+ was probably too good. They needed to spend some of their effort on the things where we gave them an F. The 2 studies on the right are the 2001 Decadal Survey and then the most recent Decadal Survey. And I actually brought copies of the popular version, and I also have a copy of the much heavier report itself. If anybody wants them, I'm not carrying them back with me, so I'll gladly hand them out. And the Decadal surveys are ultimately I think the most important documents, the most important studies that the academies do right now for the space sciences. And if you've been paying attention to what's going on in the planetary science field very closely this year, you may have noticed some extraordinary things that have happened in the political aspects of it. There was earlier this year some rather startling legislation, draft legislation that came out of Congress, which essentially cited the planetary language from the Decadal Survey and then told NASA, you will do this. And of course, we have a dysfunctional political system, so that Congress is not actually turning any of their budgets into law at the moment. But had that continued, had that gone on, you would have seen, I think, an interesting example of something it turns out that has existed for quite a long time, where the National Academy of Sciences produces a report, and then Congress tells the administration, tells the executive branch that they should be following the guidance that's established in that report. This relationship goes back a very long way. In fact, the Space Sciences Board was established before NASA. It was established a few months before NASA was. But you can go back even earlier to this very famous picture here, and that picture was actually, that photograph was actually taken in the National Academy of Sciences building downtown on the mall, if you know where the Einstein statue is. You go in that building and you can find the corner of the main atrium where that photograph was taken. And there's a great account, I think it's in the Pickering book actually, that's on the stand back there, about how after Explorer 1 was successfully launched, how the scientists, they held a press conference there, and it was 3 a.m. in Washington, D.C., and it was cold and rainy, and they were in a taxi cab coming across the river, and they expected that, you know, it's 3 in the morning, there's not going to be anybody there, and they showed up, and the room was packed with reporters. This was a very big deal. I think it's an interesting fact that, you know, this was a military rocket that launched the spacecraft, and this was an American achievement. And they could have held the press conference at the Pentagon, they could have held the press conference at the White House, but where did they hold the press conference? They held it in the National Academy of Sciences building. Now, there's a lot of reasons for that. There's a lot of symbolism to that. But it makes the point, I think, that when the American space program looks for scientific legitimacy, ultimately they come to the National Academy of Sciences to look for that, to gain that legitimacy. The Space Science Board, as I said, was established in the summer of 1958, and there was an early struggle between NASA and the academies over establishing who would be responsible for establishing the goals in space science. And they came to a rather awkward compromise that NASA, of course, would be in charge because it is the executive part of the executive branch, but that the goals would be recommended by National Academy of Sciences reports. And so soon after the Space Sciences Board was established, they stood up a bunch of different committees, and one of their committees was the right up there at the top, Committee 1, Geochemistry of Space and Exploration of Moon and Planets. Now that committee existed for a little over a decade. It was one of, I think, initially 8 that were established. And over the years has been replaced by different entities. Complex was established in 1971, existed until a few years ago when it stood down for the Planetary Decadal Survey, and has now been superseded by what we call CAPS. There was also, for a long period of time, the Committee on Planetary Biology and Chemistry, Committee on Planetary Biology and Chemical Evolution, and then that was rolled into Complex for a while, and then we had the Committee on the Origins and Evolution of Life, or SEAL, which is now, once again merged into the Planetary Exploration Committee, now as CAPS. These were the standing committees that addressed the issue of planetary science for NASA. And as I said, over the years, we've had over 90 studies that have been performed, usually at NASA request, occasionally at congressional or even OMB direction. I'm going to focus on on only a couple of key areas, in key events in the history of the program, or the history of this relationship. And the first one is the scientist-astronaut decision. In 1962, there was an Academy report, a Space Sciences Board report, that, among many other things, it addressed the broad range of space science issues, but among many other issues, it recommended that NASA needed scientist astronauts. It's actually an entire chapter in the report. It's a rather amazing chapter in the report because of the enthusiasm that comes through. You can see that these were scientists who were very much caught up in the excitement of the early space program. It's one of the few places where I've seen an Academy report that actually uses exclamation marks at points. They thought this was a great idea. And I think one of the things that struck me about this was that I was familiar with the skepticism within the scientific community. If you know about James Van Allen's comments about human spaceflight, if you know about Jerome Wiesner's skepticism of the Apollo program, it's rather amazing to see SSB report that so enthusiastically embraces the idea of space science and humans performing that. I think that what you see from this is that is kind of a middle position. This is a case where the academies, in some ways, diffused the skepticism that we saw in the broader scientific community and legitimized it in some ways. So that report came out, and I think NASA rather, reluctantly accepted the recommendation that was there. We don't. I see everybody looking skeptically as to where it's coming from. Sure hope it's not my phone. But what NASA agreed to do was to ask the academies to actually recommend space scientists to become astronauts. And so the academies held a review panel. They recommended 16 candidates. Most of them did get accepted into the astronaut program. And the key focus of this effort was, of course, to put a geologist on the moon. NASA accepted a geologist into the program and then put him as well as the other scientists, astronauts, at the back of the list. And unfortunately, as Apollo kept getting scaled back, that person actually, Harrison Schmitt, fell off the list. He was assigned to Apollo 18, and then there was, and Apollo 18 got canceled, and then there was some backroom pressure applied to NASA, and ultimately got him reassigned to Apollo 17, and he flew to the moon. I think it's a great case of the interaction between the scientific community and NASA to introduce science into the program. It ultimately did not have as great an effect upon Apollo as it did elsewhere, but there were a number of scientists, astronauts who did fly on Skylab and then on the shuttle, and it really opened up that program. And then I want to jump ahead to about a decade later to the early 1970s and the Grand Tour recommendation. Now, a lot of you know what the Grand Tour was. The Grand Tour was there's a planetary alignment that happens every 176 or 179 years. I forget the exact amount. But you can send out a spacecraft and hit a whole bunch of the planets as you fly past them, and it was a very rare opportunity. There was a big push for this mission, and yet in the early 1970s, the Space Science Board did an assessment where they produced a study where they assessed space science across the disciplines. So they looked at astronomy, at planetary science, at solar physics, and what they came to the conclusion that the Grand Tour mission was not a top priority. Now, there were a lot of reasons for this, one of which was that they were concerned about the reliability of the spacecraft, they were concerned about the cost of the mission. And, but ultimately, they did not recommend this as their top priority. And according to a contemporary account that appeared in Nature magazine at the time, this was a rather surprising recommendation to come from the academies. And yet, when the NASA budget came out a few months later, the Grand Tour mission was at the top of their list. They wanted it funded. And so they were ignoring the SSB's recommendation. What ultimately happened was that even though the budget process rolled forward, Grand Tour was approved, it then died a little later that summer. There were a lot of reasons for that, but if you go back and look at the congressional legislation at the time, the Congress specifically cited the lack of support from the SSB in killing that mission. Now, it got killed, ultimately got killed. The Nixon administration took the hint, and they killed the mission. There's a very good paper about explaining the Grand Tour mission and why it fell apart that appeared in 1997. It's got far more detail than I could ever assemble on this. But that paper by David Rubishkov, he actually cites the lack of support for this mission from the scientific community as the main reason why it got killed. It got reinstated shortly later as the Voyager missions that we all know about. They were in many ways less ambitious than the Grand Tour, and they were not supposed to do the full Grand Tour. But that experience at the time prompted Jim Green's predecessor, the person who was in charge of the planetary program in the early 1970s, to develop a kind of model for what leads ultimately to successful science missions getting approved, successfully approved. And he said that they essentially had to pass through 4 gates. And the first gate was approval from the scientific community. The second gate was approval from NASA senior management. And then Congress and OMB also had to approve these missions. But the key was, the initial key was getting scientific approval. And of course, that had to come through the SSB. And that leads me to a number of conclusions about this long history of this relationship between the two, which I think ultimately has been very beneficial over the past 50 years. I think one of the things, one of the benefits of this relationship is that it has legitimized the planetary science program. It's actually, Congress takes it more seriously because you have a bunch of eggheads with producing a report with the National Academy's logo on the cover. I think it's increased the overall efficiency of the program. There are fewer programs that get approved that ultimately fail to produce decent science. I think because they're going through a lot more scrutiny, organized scrutiny right from the beginning. I think it's helped assist in the legitimization of planetary science as a discipline, rather than a subset of geology or astrophysics. There are planetary science departments in various universities around the country, and you may not have seen that if you did not have the prestige that came from having a National Academy of Sciences imprimatur on that. I think it's increased the stability over very long periods of time. Right now, they're in the science program. You can trace back current recommendations that are being made through decades of SSB reports. You can find advocacy for things like Mars sample return in reports that came out in the early 1970s. You can find planetary protection protocols being developed in 1963. And the SSB really has, I think, contributed to the fact that these things get revisited again and again until ultimately somebody flies a mission. I think it's created a single place for advice and coordination across the scientific disciplines. For instance, how else would you get the astronomers to be talking to the planetary scientists on the issue of discovering planets around other stars, and what would they be looking for in the signatures when they're looking at that data? The SSB is ultimately a good place to do that. It's probably the only place that can really bring those communities together effectively. It's also created an honest broker. The SSB is not a NASA center. It's not representing a geographic location or a specific constituency. It's representing a bunch of different constituencies. And finally, I think it's led to better ties between the dispersed scientific community and the agency. NASA doesn't have a lot of scientists working directly for it. It has them spread all over the country. And the National Academy of Sciences, the National Academies, I've used those terms interchangeably, is a way of connecting them all. And ultimately, I think this all contributes to a better scientific program. So with that, I think I exceeded my time for about 30 seconds. So, okay, thank you.
So now we have about 4.5 minutes for questions for Dwayne, just on Dwayne's paper. Are there any questions? And please do come to the microphone and identify yourself and be considerate of others and make your question concise. Thank you.
Yes, Ralph.
Yes, Ralph McNutt, Applied Physics Laboratory. So, Dwayne, one of the things that has happened just recently in the most recent decadal surveys is that course, because of the budgetary issues that are always involved with doing these missions, there were these analyses that were done of the cost that would be involved for carrying out the program. And this is something new that the academies have sort of gotten into, looking at trying not only to look at the science, but also to look at the economics behind all of this. At least this is something that certainly didn't come up for the past several decades. And I was wondering if you could just make since now all the decadals are in, we've had all of these recent economic issues, I was wondering if you could comment on whether that looks like a good thing, a bad thing, something that's going to be in the future, or what?
Well, I think it's going to be in the future regardless of whether it's good or bad. Clearly, Congress and the administration want this to happen. It's now been enshrined in legislation saying that if you do a decadal survey, it has to include the independent cost estimation. There's actually going to be, in a couple of weeks out in Irvine, California, there's going to be a lessons learned symposium workshop on the different decadal surveys, and so that's going to be discussed a lot. I think what you've seen, there's always been a constant tension in SSB studies over this long period of time of the scientists being way up here looking at lofty issues versus getting down into the organizational nitty-gritty and the management issues. And the scientists would prefer to say, you know, here's the questions that we want to answer, go out and do that, and we're not going to get involved in the day-to-day decision-making on that. That worked, I think, for a very long time, and unfortunately now, because of cost overruns and because of the change in emphasis within the scientific community, I think that there's been a real push to actually get them involved more in those kinds of issues. I don't want to go into whether it's a good or bad idea. I think it's good if it's implemented well, but it's very tough, you know. And it's also in some ways not fair to the scientists to ask them to kind of delve into that level of detail at a very early conceptual stage.
Yeah, John Wetmore. To what extent does the international science community participate in SSB, and to what extent do foreign space programs pay attention to your reports? They
participate quite a bit when it comes to the decadal survey. We actually had a number of foreign representatives sitting on the decadal committees. As to the degree that they pay attention, I think they definitely pay attention because they have to. There's a decadal survey can come out and can wreck their own program. So they read these things intensely. They had an intense reaction to our recommendations on Mars sample return, for instance, direct impact on them. So they're involved on both accounts.
Got a really quick question?
It's a quick question. I don't know about the answer, though. That's up to Dwayne.
Yeah. Go.
So the question is, a lot of us have noticed here in this past year in particular, a trend toward dismissing decadal surveys as being of any value. This is particularly true in the planetary area. I won't name names or anything, but I'm sure a lot of folks in this room know what I'm talking about. The question I have for you is this a trend? Does this fit into a pattern that you've seen in the past? What briefly could you say about that?
I looked for trends. I had the astronomy decadal survey has been around for a very long time. And they've built up a lot of credibility over a very long time. Planetary hasn't been around as long, and so I'd be wary of drawing too many conclusions. I think give them another 10 or 20 years, and then we can decide whether or not that's really a trend. But we've only had 2 decadal surveys, and astronomy's done 6 or something like that. So I wouldn't say it's a trend yet, but that's just because I'm overly cautious.
Very much, Dwayne. And I would just ask everyone to check their pockets and their purses to make certain that all of your electronic devices are on vibrate and not on ring or buzz. Or it was a lovely chime we were listening to, but it's rather distracting for the speakers. So our next speaker is Jason Callahan. Jason has 2 master's degrees, one in international science and technology policy from GW, and another in history and sociology of technology and science from Georgia Tech. And as you already know from Dwayne's introduction, he now works for the Tauri group, but he works for Dwayne's girlfriend at NASA. So, Jason?
Good morning. So I'll be speaking today on funding planetary science. Planetary science in the United States is a public activity in that the federal government provides nearly all of the required funding, and the vast majority of that funding flows through NASA. But why does the government fund exploration of the solar system, and how does it decide the amount of money to provide to the researchers that engage in this exploration? These questions are of fundamental importance to the scientists, engineers, technicians, managers, accountants, students, and others who make up the planetary science community. Clearly, this is an uncertain time in planetary science, but is it unprecedented? The United States has suffered several recessions since the formation of NASA, and the planetary science community has dealt with limited resources and directional uncertainty many times in the past. It remains to be seen whether the current political pressures, the depth of the current economic downturn, or the increasing size of the national debt will have lasting effects on the federal budget generally, or how those effects will in turn relate to the planetary science community. But it may be informative to look back over the history of planetary science at NASA, particularly through a fiscal lens, in an effort to understand the role of planetary science as a national priority. Oops. The first thing to recognize when looking at the US economy as it relates to federal spending is that in the last 3 decades, there's little correlation between the gross domestic product and spending. That is that in the times of recession, federal spending goes up, and in times of expansion, federal spending goes up. These financial indicators over the last 5 decades demonstrate one other somewhat disturbing trend. Beginning in the late 1970s, government expenditures in red outpaced the receipts, which are in purple, consistently, and the federal debt in blue grew at a rate matching and often outpacing the rate of the increase in GDP. The result of this expanding debt is an increase in cost to the federal government in each year just to pay the interest on the debt without bringing down the principal. The cost of the interest on the US federal debt in 2010 was $414 billion, which is roughly 23 times the NASA budget that year. Now, this is not to suggest that the United States would be spending more money on exploring the solar system if it carried less debt, but it does demonstrate that an increasing debt load can place a significant burden on limited resources. And as this graph clearly demonstrates, NASA has not encountered a budgetary environment quite like this before. One of the clearest indications of national priorities is the level to which they're funded. This may seem crass, but one of the fundamental functions of government is the allocation of resources, and nearly every resource that is not money still costs money. Therefore, examining the fluctuation of funding levels in a government budget can demonstrate national priorities. Situating planetary science within the federal government is necessary for understanding the role that that planetary exploration plays in the federal government. The federal government is broken into 2 categories, or excuse me, the federal budget is broken into 2 categories, mandatory and discretionary spending. Discretionary is shown here in green. Mandatory spending involves Social Security, Medicare, Medicaid, and other programs that don't require an annual appropriations bill from Congress, where discretionary spending includes everything that does require an appropriations bill, including defense, education, energy, commerce, justice, and even NASA. The largest expenditure in the discretionary budget by far is for defense, so it's common to see budget numbers broken down into defense and non-defense discretionary categories. Here we see NASA's budget line in the context of the non-defense discretionary budget. NASA has averaged between 2 and 2.5% of the discretionary budget, and roughly 6.5% of the non-defense discretionary budget since the early 1960s. But looking at NASA since the end of the Apollo program, it's averaged less than 5% of non-defense discretionary spending. What we see here is a comparison of the non-defense discretionary line to the budget for the Department of Defense, which is in orange. If you look closely at the bottom of the graph, you'll see the budget lines for NASA, the Department of Energy, the National Institutes of Health, and the National Science Foundation. Along with the Department of Defense, these organizations receive the highest budgets in the federal government for science and technology research. I think this slide is self-explanatory. No, I'm sorry. So this graph looks at the organizations with the largest research budgets in the non-defense discretionary line. I should stress here that the term non-defense means only that these budget lines are outside of the Department of Defense and not that they're completely removed from any military application. There is, in fact, a fair amount of discourse between researchers in the civilian and military worlds, but that's outside the scope of this presentation. What we see on this graph, though, is a good representation of the shifting research priorities for the nation over the past 5 decades. In the 1960s, we see the focus on the moon landing, represented by a spike in NASA's budget in red. In the 1970s, the focus moved towards energy, and we see this reflected in the green line, representing the Department of Energy. Beginning in the late 1980s, or in the 1980s rather, and lasting for the next 20 years, we see a shift towards health and medicine in the NIH budget line, which is shown in blue. Following the spike in each of these budget lines, the general trend seems to level out a bit, give or take a few $billion. What this demonstrates is that, barring a renewed interest in space as a national priority on the scale of the race to the moon, NASA is unlikely to see a significant increase in its budget. A far more likely scenario is that the projects and programs within NASA will continue to compete for resources that are set near the current levels. Again, give or take a few $1 billion. So where does planetary science fit into all of this? NASA has averaged 1.2% of the federal budget, though this average is skewed by the massive investment in the human spaceflight program during the 60s. In recent decades, the average is below 1%. Space science as a whole, in blue here, averaged less than 20% of NASA's budget over the last 50 years, while the planetary science portion of the budget, in green, averaged about 6.5%. These averages are all a bit less if we discount the 1960s. Planetary science was the dominant portion of the space science budget in the mid-1970s. Prior to that, many of the space science efforts were attached to the human spaceflight program, and following that period, the planetary community met with increasing competition from astrophysics, earth science, and heliophysics. Between 2003 and 2006, however, planetary science enjoyed its highest level of funding ever. When we look at the history of funding for the exploration of the solar system, this graph sort of naturally divides itself into decades, with peaks in 3 of those decades and then a plateau in between. To be sure, there are not distinct breaks in the story of planetary exploration aligned with the change in decades, but dividing the story into 5 chapters helps to clarify a very complex narrative. A very brief discussion of a few of the events in each decade can help demonstrate how the interactions between NASA, the rest of the planetary science community, and government stakeholders work to establish the federal allocation of resources for solar system exploration. If the U.S. civil space program was formed as a Cold War counter to Soviet space efforts, why did the United States engage in planetary science so early in the space program, and why does such engagement continue? The answer to that question dates back to the post-war period and involves communities of researchers in fields as disparate as radio and radar research, cosmic ray research, ionospheric physics, and meteorology. Scientists in these communities began to coalesce around the idea that the data required to answer some of their most pressing questions could only be obtained by sending instruments outside of the Earth's atmosphere. A few scientific leaders in several of these space-related fields met in 1950 to determine the best path forward for their research. The outcome of this meeting was the proposal for an international geophysical year, modeled on the international polar years that were held in 1882 and 1932. The IGY took place from July of 1957 to December of 1958. The purpose of the IGY was to bring together researchers from various fields and nationalities to address fundamental scientific questions. Some of the research was not space-related, but several of the fields could benefit from instruments aboard sounding rockets or satellites. Many of the scientific questions addressed during the IGY required vast resources to acquire data, resources that were beyond the reach of individuals, academic departments, or even most military labs. By consolidating their efforts into a unified enterprise, the scientific communities were able to petition support from their governments, including military resources not normally associated with science, which led to projects like Vanguard, Orbiter, and Explorer. By the end of 1957, the space race was on, and as the United States tried to determine how best to compete. Lawmakers were consulting with many of the scientists who represented the United States during the IGY, including one prominent group of researchers who made up the Rocket and Satellite Research Panel. The RSRP delivered a proposal to Congress titled A National Mission to Explore Outer Space, which advocated a civilian organization that would allow scientists to conduct basic research similar to the experience of the IGY, but on a permanent and sustainable basis. When Congress passed the National Aeronautics and Space Act in 1958, which formed NASA, much of the language in the document echoed the proposal put forth by the RSRP researchers, placing scientific exploration at the forefront of the new space organization's mandate. In 1961, the Soviet cosmonaut Yuri Gagarin became the first person to orbit the Earth. President Kennedy determined that sending an astronaut to the moon before the Russians were able was the best opportunity for the United States to demonstrate the superiority over the Soviets in space. This decision had significant ramifications on the direction of the new space administration and on its planetary science aspirations. The moon mission became an overriding national priority, and nearly every aspect of NASA was recruited to support the lunar program. NASA's early planetary efforts focused heavily on lunar exploration, with the exceptions of the Mariner and Pioneer programs. This came as a disappointment to many in the space science community, considering that NASA, after the Mariner, or during the Mariner program, had begun planning in 1960 for a class of robotic explorers to replace the Mariner family. This new class of spacecraft, called Voyagers, would be considerably larger and more capable platforms, allowing larger science payloads. But due to several technical factors, Congress cut funding for Voyager, and NASA reallocated the remaining funds to the rising costs of its main priority, which was the lunar effort. Much of the design work for the Voyager program would appear in the Viking mission to Mars, and the name Voyager would find an entirely new project shortly. Funding for the moon mission peaked in 1967, 2 years before the success of the Apollo 11 lunar landing, and it declined through the early 1970s. For many in the space science community, however, the shift in the fortune for the human spaceflight effort seemed a natural progression. The astronauts had completed their mission, and now it was time to engage in a more robust robotic effort to explore the solar system. In 1965, a graduate student at JPL discovered a rare planetary conjunction would occur in the late 1970s. Jupiter, Saturn, Neptune, and Uranus would all be on the same side of the sun, potentially allowing a spacecraft to follow a gravity-assisted trajectory that would take it past all 4 planets. The outer planets would not align themselves similarly for another 176 years. So NASA had 10 years to plan a mission or forgo the opportunity for nearly 2 centuries. The initial mission plan became known as the Grand Tour. Planned for launch in 1979, the budget began to creep towards $1 billion, causing consternation throughout the planetary science community and Congress. Of equal importance to the budget challenges, the scientific community did not agree on what outer planets missions should take precedence. The Space Science Board, as Dwayne discussed earlier, which adopted many of the advisory functions of the Rocket and Satellite Research Panel following NASA's formation, did not fully support the mission. The Nixon administration, never a staunch supporter of the space program, favored the space shuttle over a large scientific mission, and Congress was unwilling to back a program that didn't have the support of its own scientific community. In 1971, NASA approved the Mars 73 mission, which eventually evolved into the Viking program. It beat out the Grand Tour for funding based on a lower initial estimated cost. NASA management proposed to cancel funds for the Outer Planets mission, but proponents of the Grand Tour found an unlikely ally, the Office of Management and Budget. Recognizing that this was a unique opportunity, OMB offered to restore funding to a scaled-back effort. NASA accepted, replanning the mission to include just 2 spacecraft based on Mariner designs. The proposed cost of the new mission, now called Voyager, was roughly 1/3 the amount of the cost estimates for the Grand Tour, which allowed NASA to accomplish both a deep space mission to the outer planets and the 1975 Viking mission to Mars in the same decade. We now come to the lost decade. I like this slide not only because it shows a lovely picture of Jupiter, but because the planet looks like a big 0 followed by a period, which is a good representation of the planetary science missions launched by the United States in the 1980s. Between 1974 and 1977, the planetary science budget dropped by nearly 60%. Having launched Viking and Voyager, the planetary science community expected some reduction in the budget, But by 1977, as NASA began to plan for its next planetary mission, the budgetary situation proved daunting. The new mission, initially called the Jupiter Orbiter Probe, would have to compete for a shrinking portion of a NASA budget eroded by cost overruns in the shuttle program. Strong support for another program slated to begin in 1978, a space telescope called Hubble, which had backing from the space science community, Congress, and the White House, compounded the challenging budget environment. Recognizing the difficulty of proposing two major science programs in the same year, NASA management made sure they had the backing of a unified planetary science community and worked to ensure that the Hubble supporters and the Jupiter Orbiter supporters would not sell the other side out in an effort to gain support for their respective projects. Congress approved funding for both projects, demonstrating the efficacy of the strategy and the strength of a unified space science community. Following the Challenger tragedy in 1986, the White House increased NASA's budget in order to replace the lost shuttle. The Reagan administration intended the increase to be temporary, but the incoming Bush administration decided to use the adjusted budget as the baseline to support a new direction for NASA. The budget administration wanted to push NASA to operate in a manner more reliant on innovation, taking advantage of new technologies and management concepts in order to reduce the extreme costs of spaceflight. In 1992, President Bush chose Dan Goldin as the new NASA administrator and tasked him with the mission of changing the culture from the top down. The new administrator's goal was to develop an organization less averse to risk and willing to abandon what he saw as outdated methods and thinking. Within planetary science, Goldin helped implement the Discovery Program, a class of small cost-cap missions led by a principal investigator and selected competitively from within the community. The methods Goldin wanted to implement for running the missions were characterized as faster, better, cheaper in a speech by Vice President Dan Quayle. The projects would reduce layers of management and oversight, launch within 3 years of project selection, and NASA would cancel any Discovery Program mission that went over budget. In 1995, NASA instituted the Mars Surveyor program comprised of 2 spacecraft, the Mars Climate Orbiter and the Mars Polar Lander, which would both lift off in the 1998 Mars launch window. Both missions were developed under the faster, better, cheaper rubric, but after launch, the Mars Climate Orbiter made it to Mars, but just as it was entering Mars orbit, NASA lost all communication with the spacecraft. Just six weeks later, the Mars Polar Lander arrived at the planet, and it too went permanently silent during its landing cycle. The loss of 2 Mars missions within a 6-week span did not sit well with the public or lawmakers. The accident investigation boards determined that small human errors were likely to blame for the loss of the spacecraft, but a second report issued by the Mars Climate Orbiter Board addressed the management issues that led to the error. The board found that the faster, better, cheaper strategy did not adequately assess risks in space projects. The emphasis on meeting cost and schedule placed pressures on project management to cut corners in planning, developing, and testing, and the lack of oversight meant that mistakes slipped through. In the push to change the culture at NASA, Administrator Goldin's methods seemed to have pushed too far. By the final decade of the 20th century, the U.S. planetary science community had become no more unified than any other group of loosely affiliated researchers, but they were able to find agreement in communicating their priorities to government stakeholders in NASA, the White House, and Congress. NASA commissioned the first official decadal survey from the National Research Council, delivered in 2003. That same year, NASA launched the Mars exploration rovers, and in 2006, the New Horizons spacecraft lifted off toward Pluto. The New Frontiers program selected its first candidate for the class of medium-sized missions, a solar-powered mission to Jupiter called Juno, and NASA started work on the first flagship mission to Mars since Viking, the Mars Science Laboratory, recommended in the 2003 decadal survey. Congress and the White House provided NASA's planetary science program with an unprecedented level of resources in the middle of the decade, but that level began to decline in the face of 2 wars and an economic crisis unknown in the United States since before World War II. Once more, national priorities have shifted, and the planetary science community is again faced with the challenge of demonstrating to lawmakers that solar system exploration is worthy of a significant national investment, despite a competition for resources from other sectors of governance. I just want to go back to this slide. I began researching this project with the hypothesis that members of the scientific community generally, and the space science community specifically, often did an inadequate job of communicating with stakeholders, and that this was one reason for the instability in funding seen so often in the efforts to explore the solar system. What I found was that the community actually does a very impressive job of communicating their priorities. On the whole, the lessons of the past were well learned, and most of the mistakes made today are brand new. But that's a good thing. The one place I see for improvement in communicating, both with stakeholders and with the public, is in defining planetary exploration as a national priority. Jim Green, the Planetary Science Division Director, says that the community, NASA included, needs to raise the importance of the utility of planetary science activities. And I agree. But it's not just the activities conducted by researchers in building and launching spacecraft or in the study and interpretation of the data that the spacecraft return that is of utility to the nation. It also includes the interactions of the planetary science community with other scientific communities, members of industry and academia, both here and in other countries, that provide a great benefit to the nation, a benefit that cannot be duplicated in any other national undertaking. I think the planetary science community should redouble its efforts to provide stakeholders with this perspective, in addition to the incredible scientific discoveries produced by the community's efforts. After all, given the world in which we now find ourselves, defining all of the reasons that exploration in the solar system is a national priority can only help the cause. Thank you very much.
Okay, so we have 5 minutes of questions just on Jason's paper. Again, please come to the microphone, identify yourself, and in consideration of others who want to ask questions, please be very brief. Thank you.
Mikhail Marov, Russian Academy of Sciences.
Yes, sir.
I'm just wondering, how concurrent are planetary science and astrophysics program? Because usually there are strong competition chasing between two communities. How is resolved such controversial issues? Just based on SSB recommendation or some other instruments are involved?
Well, the scientific priorities for both communities are first recommended by the Space Studies Board in separate decadal surveys. But the actual selection of missions is done at NASA through recommendations of the NASA Advisory Council and, of course, the Science Mission Directorate. And then there are divisions within the Science Mission Directorate, of course, in which I'm sorry, go ahead.
For example, Kepler, how it's regarded, like it's astrophysics or planetary science?
I see where you're going.
Just an example.
No, that's a really interesting question. And actually, someone asked me the other day about the Voyager missions, which began as planetary science, are now heliophysics missions, and very soon are likely to be astrophysics missions. So it's difficult to say. I think where I tend to draw the line is if you're able to get up close and personal to a planet, I think it falls within the planetary exploration rubric. At the moment, the exoplanet program isn't able to get us quite there. I hope that will change in the future, though I don't suspect I will see a lot of that. But at that point, I think you already see a mixing of expertise anyways, a cross-cutting of fields, and I think that will continue to increase.
Hi, Michael Neufeld, National Air and Space Museum. Congratulations on the talk. It was very interesting. I liked your graphs, and I would suggest one more, which actually follows up directly with the other speaker's question. It'd be very interesting to see the budget graph of the space science program and compared how, for example, the astrophysics, heliophysics, and planetary and biological sciences, where were the trade-offs and priorities over those decades and how that played out. And I also noted on your graph of launch noted, many of them were really heliophysics missions, but that's obviously very much a problematic distinction in many places.
Yeah, thanks. Precisely. Yeah, the definition of particularly in the early missions, what constitutes a heliophysics and what constitutes planetary, it really is sort of left up to the interpreter. I did, in fact, make some graphs having to do with the separation. I didn't have time to bring them. It's very interesting, and it's less complex in the early years when astrophysics and planetary exploration were somewhat similar. I mean, it was. You saw a lot of overlap between those budgets, which were difficult to sort of extract from each other in the early years. In later years, it becomes far more complex as you have more players. But you're absolutely right. It is a fascinating story.
All right. Well, thank you very much.
Thank you.